Hi, sixth graders. We are on our second lesson in Unit 10, so you can add this on right after your notes from that first video that you watched. This one is on sample spaces and fundamental counting principle. Sample space is a word and a definition that you want to write down. So sample space is a set of all possible outcomes or results in an experiment. Two different ways of finding sample space is tree diagrams and fundamental counting principle, which we're going to go through as we go through this video. All right, so let's look at this common example of going to the ice cream store and ordering an ice cream cone. So if there are choices between vanilla and chocolate ice cream, waffle or sugar cone, and hot fudge or caramel, and we want to find the sample space. So the sample space is how many different outcomes are there, or how many different total choices are there of getting one scoop of ice cream in a certain kind of cone with one topping. So this is a table that shows all of our different choices. So we can see we can get vanilla in a waffle cone with hot fudge. We can get vanilla in a waffle cone with caramel. We can get chocolate in a waffle cone with caramel. We can get chocolate in a sugar cone with caramel. We can get vanilla in a sugar cone with hot fudge. So then if we count, we can see we have 1, 2, 3, 4, 5, 6, 7, 8. So our sample space, which means how many total different options are there of ordering, is 8. Okay, so sometimes writing out a table like this works when there's not a ton of options, like 8 is a small sample space. Other times, using a different method would be more efficient. So instead of making a table, we could make a tree diagram, which eliminates some of the writing of each category and still allows us to figure out the sample space. So we can see that we have, if we look at this example, the animal shelter has both male and female Labradors in yellow, brown, or black. Find the sample space for all possible Labradors at the shelter. Well, our first choice is male or female. So I'm first going to write male, female. And up here I'm going to write my gender, because we're going to pick between gender and color. My second choice then is, do I want yellow, brown, or black? So I know that I can get a male yellow, male brown, and or male black. I can also get female yellow, female brown, female black. So I'm just eliminating writing male yellow, male brown, male black. I can just write my gender one time and then add on from each gender all of the outcomes. This is an example of a tree diagram. Now if I go over here, I can count. I have 1, 2, 3, 4, 5, 6. So my sample space here is 6. I have 6 total different puppies that I can choose from. And then I can look at it just like my table. I can pull out certain outcomes that we want. If I look here, this tells me I'm getting a male yellow Labrador. I could look here, and this tells me I'm getting a female brown Labrador. So then I can pick out each outcome if I would like, but based on these options, I have 6 total different outcomes that I can pick from in this scenario. Okay, so here's another option of us using a tree diagram. We have a car that comes in silver, red, or purple as a convertible or a hardtop. How many different combinations of cars are there to choose from? So when we set up our tree diagram, we want to make sure that we think about the different choices that we have. So one of our choices is color, and the other choice is the kind of, I'm just going to put kind of car for a convertible or hardtop. So then that helps keep me organized with my tree diagram. And if you have more choices, you're going to need a lot more room and you want to space them out just a lot more. But for color, I have silver, red, or purple. And then for the kind, we have convertible, hardtop, convertible, hardtop, convertible, hardtop. Notice how I'm adding it on again from each combination or each choice from before. Then I can count. So I have 1, 2, 3, 4, 5, 6. So my sample space is 6. And then it says, what's the probability of choosing a purple convertible? So if I find purple convertible, so here's purple, here's the convertible. I don't see any other ones that have a purple and convertible together in the same option. So there's one choice for me to get a purple convertible, and there's 6 total outcomes or 6 total choices. So the probability is 1/6. And then I can change that to a decimal, so 0.1666 repeating, which I would round it to 17%. So the probability is a 17% chance of getting a purple convertible. Okay, so one more example of using a tree diagram in a situation. So if we're at the deli and we can choose from the salad bar, wing bar, or soup bar, and then we can get a bun or a breadstick, and for dessert, we can get pudding or a slice of pie. What are the combinations of meal options? So I didn't leave myself enough room on this page, so I'm going to go to the next page and show you how I would write this out as my tree diagram. All right, so our first choice is which food bar are we going to choose from? Then which type of bread? Then dessert. So I'm going to leave myself quite a bit of room because it tends to get kind of squished in there. So I can choose between the salad bar, the wing bar, or the soup bar. Then I can choose between a bun or a breadstick from salad, and then for wings, bun, breadstick, and then I can get soup with a bun or soup with a breadstick. Then my last choice is dessert. So I could get a salad, bun, and pudding, a salad, bun, and pie. I could get a salad, breadstick, and pudding, salad, breadstick, and pie. So I'm going to keep adding on both of my choices from each of these. Notice how I'm keeping it nice and organized and clear so I don't miss any of my choices. If you try to cram this into one tiny line on your page or a few lines, you're going to miss some of the choices. So like I did here because I was trying to talk. All right, so then I can go through and I can count how many total outcomes do I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my sample space is 12. The question on the previous page said, what is the probability that I pick salad bar? So let's look and see how many options here have salad bar. Well, these all have salad bar. That means all of these include the salad bar. They either include a bun or a breadstick, but they all include the salad bar. So that means I have 4 options. So probability of getting salad bar equals 4 out of 12 because there's 4 choices with the salad bar and there's 12 total options, which is 1/3, which we know then is 0.3333 or 0.3 repeating, which we make as 33%. All right, if Marcos tosses 3 coins, if all 3 coins show up heads, then Marcos wins. Otherwise, Kara wins. Find the sample space and then find the probability that Marcos wins. All right, so he tosses 3 coins. So if he tosses 1 coin, so we have coin 1, we have coin 2, and we have coin 3. The first coin that he flips, he can either get a heads or tails. When he tosses the second coin, he can again get heads or tails. So I'm going to add that to my first coin. So now I know the second coin, he can get heads or tails. And then the third coin, again, heads or tails. But notice how I'm adding it on to each of the previous outcomes that we had said. So with this combination of throwing 3 coins, I can see that we have 1, 2, 3, 4, 5, 6, 7, 8 different options of what he would get if he throws 3 coins. We know that there's only 2 outcomes throwing a coin, a heads or a tails, but the number of outcomes changes the more that he tosses more coins. So if I look here, just to read this tree diagram, this right here would be tails, tails, tails. This right here would be heads, tails, tails. This right here would be heads, heads, heads. So see how you can see each outcome, because if you flip 3 coins, you would get the same possible outcomes. You could get heads, heads, tails. You could get heads, heads, heads. You could get tails, tails, heads. Okay? So if all 3 coins show up heads, then Marcos wins. So here's our heads, heads, heads right here. That is the only outcome. That's 1 out of the 8 that he can get to win. So his probability that Marcos wins is then going to be 1/8, because only 1 out of the 8 outcomes has heads, heads, heads. Okay, a different way of finding sample space, which is a little bit quicker, is called the fundamental counting principle. So please pause and write this word down with this definition. So if event 1 has m possible outcomes and event 2 has n possible outcomes, then event 1 followed by event 2 has m times n possible outcomes. So basically, we're just taking the number of possible outcomes for each event and multiplying them together. So if we have find the total number of outcomes when a coin is tossed and a number cube is rolled. So the coin and the number cube, which is the dice. So the coin has 2 outcomes, because remember it can be heads or tails. The dice has 6 outcomes, because it can be 1, 2, 3, 4, 5, 6. If we multiply them together, 2 times 6 is 12, so 12 total outcomes. So notice this is based on how many outcomes? 2 outcomes, 6 outcomes. Find the total number of outcomes when choosing from bike helmets that come in 3 colors and 2 styles. So we have colors and styles. There's 3 colors, 2 styles. Multiply it together, we get 6 total outcomes. The jeans shop sells young men's jeans in different sizes, styles, and lengths as shown in the table. Find the number of jeans available. Well, I can see here for the waist size we have 1, 2, 3, 4, 5. Here we have 1, 2, 3 for the length. And then for the style, we also have 3 choices. So notice I'm just counting how many choices for each category, multiply them together. So 5 times 3 is 15. 15 times 3 is 45. So that means there's 45 total possible outcomes that you could walk away with between this waist size, length, and style. And then it says, find the probability of getting a 32 by 34 slim fit. So 32 by 34 slim fit is just one of the options out of the 45, so the probability of getting that would be 1/45. Okay? Find the total number of outcomes when a coin is flipped 3 times. So we need to think of coin 1, coin 2, and coin 3. The first thing that a lot of people want to do is we think, oh, a coin has 2 outcomes and it's being flipped 3 times, so we do 2 times 3 and we get 6. But if we think about it, the total number of outcomes when a coin is flipped 3 times, well, we have to think of how many outcomes each time it's flipped. So coin 1 has 2 outcomes because it's heads or tails. Coin 2 has 2 outcomes because it's heads or tails. And coin 3 has 2 outcomes because it's heads or tails. So we multiply these together. Oops. And we get 2 times 2 is 4 times 2 is 8. So we actually have 8 as our total number of outcomes. So we have to stop and think about what it is asking us. Similar situation here. Find the total number of outcomes when a dice is rolled 2 times. So dice 1, dice 2, or roll 1, roll 2. The first time we roll it, we have 6 outcomes. The second time we roll it, we still have 6 outcomes. So we're going to do 6 times 6, and we get 36 total outcomes. Not 6 times 2, because it's rolled twice. 6 times 6, because we have to think of the number of outcomes each time it is rolled. All right, I would like you to do these problems at the bottom of your notes. Please make sure when you submit your notes, if there's a way for you to submit your notes and these questions, that would be great. Whether you have to take 2 pictures or if you can try to get them all into 1 picture for me to see your notes and to see your work. Read the questions carefully so you know what it's asking you. Go back in the video and rewatch some examples if you're not sure how to do them. And then make sure you go back to today's folder so that you can upload and submit your notes. Have a great day, everyone.